right, this is 3.5 part 3. We're going to be looking at stretches and compressions and then kind of putting everything together that we've gone over in the last few videos. So vertical stretch or compression of the graph of a function. Suppose that a is greater than 0, so a is a positive number. If a point x, y lies on the graph of y equals f of x, then the point x, comma, ay lies on the graph of a times f of x. So what they're saying is if you multiply that number times the whole function, then you're multiplying that y value times the function. Well, we know that f of x is just another name for y, so that makes sense that you are multiplying the y value by a. And that's how the graph changes. If absolute value of a is greater than 1, so all that's saying is a is a whole number. The absolute value of a is greater than 1. So it doesn't matter what the sign is, take the sign off. If it's greater than 1, then the graph of y equals a times f of x is a vertical stretch. Of the graph of y equals f of x. So think vertical, that's up and down, and stretch, so it's going to elongate in the vertical direction. Now if a is between 0 and 1, the absolute value of a is between 0 and 1, that's talking about fractions. So a is a fraction. Then the graph of y equals a times f of x is a vertical compression. Of the graph of y equals f of x. So compression, so think that vertical direction again, up and down. Compression, you're squeezing it in. And so it's going to become shorter, which then makes it look a little bit wider, actually. And again, you are multiplying the y value times whatever that a is, whether it's a whole number or a fraction. You're multiplying the y value times that number. So think if a is a whole number and I multiply y by, let's say, 2, then each y value is going to increase by a multiple of 2, thus making it taller, which will make it look skinnier. Versus if a is a fraction, like 1/2, and I multiply the y values by 1/2, each y value is going to become smaller, and thus making your graph compress vertically. All right, now let's look at horizontal stretches and compressions. Suppose that a is greater than 0. Okay, it's a whole number. A positive number. If the point xy lies on the graph of y equals f of x, then the point 1 over x, so you're multiplying x by the reciprocal of that number. Then that point lies on the graph of y equals f times a f of a times x. So notice they're multiplying the a by the x on the inside of the function versus multiplying the a on the outside of the function. Okay, if absolute value of a is between 0 and 1, so that is a is a fraction. If a is a fraction, then it's going to be a horizontal stretch. And that's because you're taking the reciprocal of a and multiplying it times the x value. So if a is a fraction, and then I get the reciprocal of that, it's going to be usually a whole number, but let's say let's say for instance, a is 1/2. The reciprocal of that is 2. I'm multiplying x by 2. So now each x value is increasing. It's getting larger by a multiple of 2. So it's going to stretch horizontally. And then if the absolute value of a is greater than 1, so a is a whole number, then the graph of y equals f times a of x, f of a times x is a horizontal compression. So it's going to be squeezed in horizontally. All right, let's just take a look at Desmos to try to get a better visual of what's happening. All right, so here I have the absolute value function, and I have created a slider for a, and then I called the one inside the function b. So the a on the outside here, that's going to cause your vertical stretches and compressions. It's being multiplied by the whole function. And then if it's on the inside of the function, that causes your horizontal stretches and compressions. So b is going to be causing horizontal stretches and compressions. All right, so let's see what happens if I make a positive whole number. As I increase a, notice the graph looks like it's just becoming skinnier, but think of vertical stretch. It's being pulled up. Being pulled up. Okay, and then if I make a fraction right here, a number between 0 and 1, so here it is originally with no transformations, then I change a to a fraction, it's being compressed vertically, it's being pushed down, becomes flatter. Now if I make it a negative, then we get that reflection we talked about yesterday along with the compression or stretch. So a negative number less than -1, it's going to give you the vertical stretch, but also it's reflected. It's being stretched out, but it's also reflected. And then a fraction here between 0 and 1 is going to give me the vertical compression, but also a reflection. All right, let's look at what b does. Let's see the comparison there. Okay, so b, I'm going to make it a whole number greater than 1. Okay, and notice as I make b greater, it's being horizontally compressed. For whole numbers, it's going to cause a horizontal compression. It's being squeezed in on the sides. Now, if I make b a fraction between 0 and 1, that causes a horizontal stretch. So compared to the original, here's the original, that's the parent function. If I change that b to a fraction between 0 and 1, it stretches out horizontally. Now, if I make b negative, it actually still looks the same as when it was positive, and that's because, remember, yesterday we talked about even graphs. Since absolute value is even, that means it's symmetric across the y-axis. Even if you reflect it, if you do a reflection over the y-axis, it's still going to look the same. So if I make b a negative number, no effect. Here's positive 1, here's -1, no change. That's because it's even. All right, moving right along. Let's look at some examples. Identify the transformations, make a table for the transform points, and graph the function. So let's identify our transformations. A 2 outside of the absolute value, so this is in front of the function, that is going to cause a vertical stretch. By a factor of 2. So each y value is going to be multiplied by 2. So you could say each xy is going to become x comma 2y. So let's graph our parent function. Okay. Now, I'm going to multiply each y value by 2. So instead of 0, 0, well, 0 times 2 is still 0. But right here, multiplying the y value times 2 puts me at 1, 2. And then right here at 2, 4. Y value is 3. Multiplying that by 2 gives me 6. And so on. And then on this side, multiplying these y values, so the y value right here is 2, it becomes 4. The y value here is 5, so it becomes 10, multiplying it by 2. Oops. All right, so there is the graph of the transformed function stretched vertically by a factor of 2. Making a table of the transformed points here, really that's just to help you graph it. So if this is enough to help you, you can use that. Otherwise, what you can do is just make a table of those points. So for example, the original function, the parent function, is going to have -2, 2, -1, 1. Remember, each y value is just the absolute value of the x value. And then for the transform point, I'm taking the y value and multiplying it by 2. So the x value stays the same. The y values get multiplied by 2. So if you can't graph that just by looking at the graph, you can always just draw some tables out and then plot those points. All right, next one. This time our 4 is on the inside of the parentheses, so it's inside the function. So this one is going to be horizontal. It's a horizontal and it's a whole number, a number greater than 1. So that's going to be a horizontal compression. When it's a whole number, it compresses. Horizontal compression. And that's going to be by a factor of 1/4. Just like you're multiplying your x value by the reciprocal, the factor by which it's compressed is going to be the reciprocal. So you could also do your x comma y is going to go to 1/4. We're multiplying that by the x value this time because it's inside with the x value. 1/4 xy. All right, so the parent function for the quadratic. You could draw your table out here if that helps you. Let's see, that would be -2. -2 squared is 4. -1 squared is 1. 0 squared is 0. And so on. Multiplying each x value by 1/4, it's going to give me some fractions. My y values are not going to change. Okay, so 1/4 times -1 is -1/4, 0, 1/4, and 1/2. All right, so then I can graph that. You don't even have to graph the parent function in that case. Okay, so I've got -1/2. I'm at 4. At -1/4, I'm at 1. I know that's hard to graph. Just get really close to the y-axis. Okay, at 1/4, I'm at 1. At 1/2, I'm at 4. So very skinny parabola. You could get more points if you need to. But the moral of the story there is we've got a horizontal compression by 1/4. it has become very skinny parabola. All right, number 15. This one, the 1/2, is on the outside of the function. I know that because there's no parentheses here. That would make it horizontal, but this is going to be vertical. It's going to be a vertical compression because it's a fraction. By 1/2. So you only do the reciprocal if it's horizontal. And it's horizontal if it's inside the function. All right, so you could do the table, let's see, x, y, for the parent function is going to be -2, -8, -1, -1, just cubing each x value to get the y value. Okay, and that's going to go to, so if it's a vertical compression, you're going to be multiplying the y value, so x comma 1/2 y. So the x values don't change. The y values get multiplied by 1/2. Or, like I said earlier, you can sketch the parent function if you'd rather do that, and then perform the transformations. Okay, so that's -2, -4, -1, -1/2, 0, 0, 1, 1/2, and then 2, 4. Remember the shape of the cubic function? Okay, there it is. Looks pretty similar to your parent function, but it did get vertically compressed by 1/2. All right, next page. All right, now we're putting them all together on this page, applying more than one transformation at one time. To do this, you want to go from left to right. So let's first look at this negative. That negative on the front is going to cause a reflection over the x-axis. Then I have a +3 on the inside. That's your h value. It's going to make you go left 3. +1 on the outside is going to make you go up 1. So I have these tables here for us. Let's write out the points for the parent function for quadratic, and then we'll get our transformed function. So parent function is going to have these points. The y value is just the square of the x value. All right, so now to transform it, what do we need to do? First, it gets reflected over the x-axis. So remember, anything on the outside of these parentheses is affecting the y value. Anything on the inside is what's affecting the x value. So that negative is going to be multiplied by the y, because it's on the outside of the parentheses. And then that +1 at the back is going to be also added to the y, just like that. Now the 3 is on the inside of the parentheses, and so you're going to do x -3 there. Always the opposite sign. It makes it move in the opposite direction. So x -3. So now we can get our new points. It's very helpful to do tables when you have multiple transformations going on at once, because it can be a little tricky to do all of that work on a graph. So let's see, that'll be -5, -4, 0. Oops, sorry, not 0. -3. I think I was multiplying in my head. -2 and -1. Now, -y +1. So -4 +1, -3. -1 plus 1, 0. 0 plus 1, -1 plus 1, and -4 plus 1. All right, so those are our new points. Let's put them on the graph and see what it looks like. -5, -3, -4, 0, -3, 1, -2, 0, and -1, -3. All right, there's your parabola. Got reflected over the x-axis, so it's now upside down. It shifted left 3 and up 1. All right, we've got absolute value here on the second one. The transformations. So on this one we have to be careful because remember your standard form always has f of b x minus h, something like this. So that coefficient there needs to be factored out of the x minus h. So I'm going to factor that 2 out, like so. All that does is going to change how much your graph moves left and right. So if you hadn't factored it out, you would have said, oh, it moves to the right 4, but actually it should just be moving to the right 2. So that 2 on the inside of the absolute value is going to be a horizontal compression by 1/2. And then the -2 is going to make it move to the right 2. Okay, let's get our parent function right here in the first table. So -2, -1, 0, 1, 2. Typically what I start out with for the x values, unless I need perfect squares or perfect cubes to be there for the square root and cube root functions. All right, so the x, anything on the inside is what affects the x. So the 1/2 gets multiplied by the x, and then it moves to the right 2, so that's +2. Basically, anything affecting the x is always like opposite. I think of it as it's always just backwards, right? So because there was a 2 here to begin with in front of the x, now it's a 1/2. And then there was a -2, it became a +2. So you're always changing things involving the x, never things outside of the function that affect the y. So 1/2 x plus 2. 1/2 times -2 plus 2. 3. Oops, sorry, not 3. 1. Oh gosh. -1/2 plus 2 is 3/2, or 1.5. And then we've got 0 plus 2, 1/2 plus 2, 2.5, and 1 plus 2. So those are your new x values. Your y values are not going to change. All right, let's put that on the graph. We're just graphing those new points. I've got 1, 2, 1.51, 2, 0, 2.51, and 3, 2. Very small little v there. That's because it got compressed horizontally. That's why it looks so narrow here. I have a hard time drawing a line like that. Anyways, that is your transformed absolute value graph there, with a horizontal compression of 1/2 and shifted to the right 2. All right, number 18. All right, so this, we're going from left to right still. This 2 on the outside, that's not inside parentheses or anything with the x, so that's going to be a vertical stretch. By 2. And then the -5 at the back, that's going to be your k value, which makes your graph shift down 5. Okay, so my parent function here, we've got -2, -8, and all of these points. Okay, there's some standard points we can start with. Now, if it's being vertically stretched by 2 and shifted down 5, those both affect the y value. So you're going to say this is 2y minus 5. Remember, I said nothing's backwards when it comes to the y value or the vertical stretches and compressions and whatnot. You just straight up put that 2 times the y value and then -5. And that's how your graph is going to be affected. That's how each point will be affected. All right, so those are my new points. Put them on the graph. -2, -21. Can't exactly put that one on the graph, but it's going to be way down here. And then I've got -1, -7. 0, -5. 1, -3. And 2, -1. Oh, I don't know what I did here. That's definitely not right. I think I was plugging the 2 in. Okay, but I should have been plugging in this 8 here. 8 times 2 is 16. 16 minus 5 is 11. So this one should be, I knew something was wrong with that. There we go. Up at 11. Then I know what this graph should look like, because I know what the cubic parent function looks like, and then it's just vertically stretched and shifted down. So there it is. All right, graphing translations of a given graph. So a graph of a function defined by y equals f of x is shown in the figure. Use the graph to sketch each of the following graphs. So we're going to use this graph and these functions with the transformations to get the new graph. So on number 19, I've got a -2 on the inside. That's making my graph go to the right 2. And then the 3 is going to make it go up 3, that +3 at the end. So I've originally got this point -4, 0. So I'm going to shift it up 3 and to the right 2. So right 2, up 3. There's my new point there. And then I could also do this point at -2, 2. That's where I start, but I need to move right 2 and up 3. And then I got 0, 0, move right 2, up 3. Okay, so there gives me that little parabola shape that we have at the beginning. Then let me do this point here at 1, -4. So I'm just taking them one at a time and performing the 2 transformations, moving it to the right 2, up 3. And finally, I've got 3, 0. I'm moving it to the right 2 and up 3. Okay, there it is. There is f of x -2 plus 3. Okay, what about number 20? So we've got a reflection over the x-axis. The 1/2 causes a vertical compression by 1/2. And -4 makes it go down 4 because it's on the outside of the parentheses. So if you wanted to do your coordinates, that would be reflection over x and the 1/2, all three of those things. They're all outside of the function, so they all only affect the y value. So your y values are going to be -1/2 of the original y and then -4. Okay, so let's take that first point, which is -4, 0. I could have done it like this on the last one as well. The x value is not going to change. The y value gets multiplied by -1/2 and subtract 4. So I'm going to have a point at -4, -4. Okay, next point. -2, 2. That point is going to get, the x value is not going to change, but I've got -1, -4 is -5. So -2, -5. Zero, 0. The 0 won't change. That gives me -4. So 0, -4. Okay, notice you can already see that vertical compression happening. That parabola looks much flatter, and then also it's reflected. It's upside down now. So next point, we've got 2 more points to do. We've got 1, -4. There we go. So at 1, -2. And then my last point is 3, 0. So that's going to go to 3, -4. All right, there it is. There's h of x with all 3 of those transformations. All right, now let's try going in a different direction. We're actually going to write the equation for each of the functions. So you're going from the graph to the equation. First of all, on 21, this is going to be quadratic. So it's going to be your x squared function. It looks like I didn't have any stretches happen because I still have just like 1 squared is 1 and 2 squared is 4. 1, 2, 3, 4. Okay, so it still goes up the right amount if you think about it that way. But it did shift to the right and down. So let's just write a function here, f of x equals x. They move to the right 1. I'm going to write my transformations here. Right 1. And so what is that going to do to my function? It's going to make me subtract 1 on the inside of that function. And then it also went down 3, just looking at the vertex. So -3. Next one, I've got absolute value. Notice the slope is still 1 and -1, so no vertical stretches or compressions. It's still facing up, so no reflections. And so we're just looking at some shifts, some translations. So it looks like it shifted left 2. I'm just looking at the vertex. It also shifted up 2. So absolute value On the inside, we need to go left 2, so x plus 2. And then it goes up 2, so plus 2. And this last one, that is the square root function. Remember the square root function, the parent function looks like that. So this got reflected over the y-axis. And then it, no other transformations actually. No shift up, down, no, nothing else. So just reflected over the y-axis. So remember, when it's reflected over the y-axis, that means you're multiplying your x by a negative. You're multiplying the inside of the function by -1. So this will be f of x equals square root of -x. That negative makes it reflect over the y-axis. All right, the next page is really just a summary of everything we've done over the last few days. So I'll fill that in, and then if you want to copy it down, you can.